So in the early of this class, we we know that for the lag compensator, for the lead compensator, we can use higher gain, but still secure the damping ratio of the system, and it can provide a fast response, but still don't have the overshoot. But the problem, we still see the steady state error. So our hint is maybe the lag compensator, which is similar to the PI, maybe can help us reduce the steady state error. But before we jump into the MATLAB, we may try to review the idea of the steady state error from the block diagram. Maybe this system have the transfer function as shown, and the system is type 0. So just only unit step input, maybe we're gonna have some steady state error with this system if the controller is just a proportional control. So the block diagram that we can draw, for proportional control, and the plan and the output, the reference and feedback. The error at this point is what we are going to focus on. By the summing block here, the error in the Laplace domain is equal to the reference signal subtract by this one. The feedback one equal to the error multiplied by K and multiplied by the plan because our feedback, the sensor transfer function, the ideal sensor transfer function is 1. So the error itself plus gain K multiplied by the plan equal to the reference, and when we derive the error in terms of the reference input, for a unit step input, and the plan transfer function is this one. If the system have a unit step input, Rs is 1 per S. The time domain, the time domain steady state error can be obtained from the final value theorem. The error in time domain when time approach infinite, or the steady state error, is equal to the limit of S to 0 of S multiplied by ES. Final value theorem. So if the input is ramp, no, if the input is step, we have limit s to 0 of s multiplied by 1 per k and s plus 1, s plus 2, and input we have the same, we multiply all the term by this denominator. When s close to 0, when s close to 0, we have 2 per 2 plus k, 2 per 2 plus k as steady state error, as steady state error. So let's see what should be the value of k. What should be the value of k for proportional control? For proportional control. Here is steady state error. For proportional. If we need to decide the gain k for the system so that we can achieve the desired damping ratio, we need to use the root locus to find the gain k that the system still have the damping ratio 0.7. If we use the root locus, and proportional gain, the open loop transfer function is this one directly to be this one because controller just proportional. So let's plot the root locus of this one. We don't have 0. We have pole at -1 and -2. We have pole at -1 and -2, and we don't have 0. So the root locus of this system, we have two asymptotes in positive and negative 90 degree. And the breakaway point directly at 1.5, -1.5, in the middle between -1 and -2. And along the root locus, we decrease the damping ratio when the gain getting higher. And our requirement is damping ratio 0.7. At that point, the gain that we can use for proportional control, is 2.49, and we still secure the desired damping ratio. And with the gain k 2.49, what should be the steady state error? It should be about 0.45, How can we confirm this How can we confirm this? We already decide the gain k, right? We already decide the gain k. 2.49. And we have the plan. And we have output. We have input. So to plot the step 6, it should be the closed loop transfer function. It should be the closed loop transfer function. And the closed loop transfer function can be obtained from the command feedback of the open loop. Gain multiplied by 6. And the feedback is 1. So closed loop transfer function use the command feedback, gain multiplied by the transfer function gs, and the feedback is only 1. So the sys itself, when I plot the root locus, the sys is the transfer function of 1 and convolution s plus 1, s plus 2. So the sys or the system transfer function gs is this one, second order polynomial. The root locus of sys for the open loop transfer function, we have the root locus. We already picked the gain k. But to plot the response, we need to plot the response of closed loop. Closed loop means 6CL. I name 6CL. So for the closed loop transfer function, we have the gain multiplied by the system transfer function, and the feedback gain is 1. And we have the closed loop transfer function. The step 6CL. So for the step 6CL, the response seems promising. The vibration is not so ugly. Just a small overshoot. And the response is not so slow. But the main problem is, don't forget that our reference command, the step response. Our reference command, the value is 1. But the steady state value of this response is just 0.55. The error is equal to 0.444, about 0.44, 0.45, 0.44, which is agree with our derivation of the steady state error, The suggestion now is, what if we add a lag compensator? To the system? Instead of using only the gain k, but we have k s plus 0 divided by s plus 4. S plus 0 divided by s plus 4. and the original system. The error of the feedback system, if we derive the block diagram, again, the error of the feedback system gonna equal to 1 per 1 plus k. If this is a lag system, it's gonna be s plus 1.5 divided by s plus 0.15. The lag compensator, and then the system. And multiply by the unit step input, The error of the feedback system in the S domain, 1 per 1 plus the feed forward. No, the loop. But the feedback is equal to 1. So we have only the lag compensator and the system transfer function. If we need to derive the steady state error in time domain, we need to apply the final value theorem again to this one. So please remember this one. The error equal to 1 per 1 plus k, and the lag compensator s plus 1.5 divided by s plus 0.15, and multiply by the system transfer function s plus 1, s plus 2, and the input. So for a unit step and the time domain steady state error, we use the final value theorem. And unit step input. So when S, I should multiply all the term by this denominator. So in the numerator, we have S plus 0.15 multiplied by S plus 1 and S plus 2 denominator, we have s plus 0.15, s plus 1, s plus 2, and then we plus by k, s plus 1.5. When s equal to 0, we have 0.15 multiplied by 2 divided by 0.15 multiplied by 2 and plus 1.5k. 1.5k. So what should be the gain k? What should be the gain k in this case for the lag compensator? What should be the gain k that still secure the damping ratio? We plot the load locus. By using the open loop transfer function. The open loop transfer function is the controller, the lag compensator, multiplied by the plant transfer function. This controller, CC, transfer function of controller, is transfer function of S plus 1.5 divided by S plus 0.15. This one, the controller, is the same with the transfer function. Open loop transfer function is controller multiplied by the system. The load locus, we plot the load locus from the open loop transfer function. So if we come back to see the open loop transfer function now, we have GOS, open loop transfer function. We have S plus 1.5 divided by S plus 0.15 and the system transfer function. We have 0 at minus 1.5. We have pole very close to the origin, minus 0.15. Another pole, minus 1. Another pole, minus 2. And the load locus will be on the left-hand side of the first and the third pole and 0 on the real axis. And we have 1, 0, and we have 3 pole. We have 1, 0, and we have 3 pole. So the asymptote gonna be plus and minus 90 degree. Asymptote gonna be plus minus 90 degree. The intersection point between asymptote and the real axis gonna be summation pole minus summation 0 divided by n minus m. The alpha summation pole minus summation 0 divided by n minus m. And in order to secure the damping ratio 0.707, the possible gain K is 0.9. The possible gain K is 0.9. This gain K, 0.9. And in order to see the response, yes, we have the gain K. สักครู่นะครับสอนหนังสืออยู่จะกลับแล้วเหรอครับหรือว่าไงแป๊บหนึ่งรอสักครู่ครับเดี๋ยวผมเดินไปหารอตรงนั้นแหละ I will come back. Okay, sorry, let's continue. So we see the MATLAB code to compose the closed loop transfer function. To compose the closed loop transfer function, we use the command feedback, and we use the gain that we obtain from the root locus, and we multiply by 6. I think, not sure if I do something wrong here. It seems like it should be 6O. Because we obtain the gain K from the root locus, and the gain K that we obtain from the root locus, wow, it seems like I have something wrong here. Wait a second, the slide is wrong. Let me see the MATLAB. Wait. I'm not sure I still have it in the MATLAB. The correct one should be the gain. Oh no. 2.49. Wait a second. 0.902. .49 and 0. I'm not sure if you still can see the MATLAB now, but the correct one should be it should be this one. So in the MATLAB, if you need to follow, this line is wrong. This line is wrong. You need to compose the CCL or the closed loop transfer function by the command feedback. And the gain that we use gonna be 0.9 multiplied by the open loop transfer function. The open loop transfer function means the controller transfer function multiplied by the sys transfer function. And the feedback gain is 1. The feedback gain is 1. You should use this CCL and then you plot the step of the CCL. The plot is correct. The plot is correct, but the command here is wrong. The command here is wrong. And the value, when we see the value, the magnitude here is 0.82, 0.82. It means the steady state error, gonna be one minus 0.817. When we use this gain value, and we try to compute the steady state error, it should be the same value. But I still didn't check. So if you have time, try to confirm that the steady state value that we obtain from the derivation should be equal to the one that we found in the plot of the step response. Okay, we already know that maybe with the lag compensator, we can reduce the steady state error from 0.45. 0.45 accuracy is like extremely bad. I mean, the reference value is 1, but the response is 0.55. It's just only half in magnitude compared to the reference value. But with the lag compensator, we have the error about still be like 18%. Not perfect, but better than nothing. So what we are going to do next is, in our previous derivation, when we see that the lead compensator can provide a good response compared to the reference, the lead compensator better than the original system, better than the P control and PD control. But only one problem is we still have the steady state error. Our system, original system, the system is type 1. And the input, if the input is step input, of course we can guarantee 0 error. But if the input is RAM, we have some steady state error. And although we already include the lead compensator, we still have the steady state error. How can we improve this system? By the lag compensator. The original system the steady state, no, the error is the reference minus error multiplied by controller. Maybe if we separate K to use the root locus, K can be the one that multiplied to the plan, or K can be the one that multiply between the compensator, is the same meaning. And the error 1 plus K D G equal to the input, which means the error itself is 1 per 1 plus K D G multiplied by the input. For a RAM input, for RAM input, one per S square, the steady state error S multiplied by the ES we have the lead compensator from our first example, and we have the system also from our first example. And the input is RAM. Seems like we have one S in the denominator. So S will be like multiplied to 1. And S, when it multiplied to this term, it's gonna cancel with this one. So we have K S plus 2 divided by S plus 20 S plus 1. When S equal to 0, it's 1 per, oh, sorry. when s equal to 0, 2k divided by 20. So it depends on the gain k. It depends on the gain k. If we use only the lead compensator and we want to get a small steady state error, we may need to increase the gain k. We may need to increase the gain k. But the limitation for increasing the gain k, we need to check the root locus and consider our acceptable damping ratio. We can increase the gain k. At this point, the gain k is about 31 and the damping ratio 0.7. In the previous slide, we know that by the phase lag, it seems like the lag compensator can have benefit in terms of the steady state error. This system is not that bad by only the lead compensator, but if we want to improve the steady state error by add the lag compensator, before we do that, we may just see if we have the lag compensator. If we have the lag compensator, we put more the lag compensator here, and we have lead and lag. What's gonna happen? So we're gonna begin from this line, but just add the lag compensator S plus 0.1 per S plus 0.01 to this and see what's gonna happen to the steady state error. One per 1 plus k, and we add the lag compensator. S plus 0.1 and S plus 0.01. Original system already have the lead and the plan. And don't forget the RAM input. Which means we're gonna have one S that multiply to all the terms of the denominator. S multiplied by 1. And when this S multiplied to 1 per S, it's gonna cancel. And we have K. And S plus 0.1 per S plus 0.01. S plus 2 per S plus 20 and 1 per S plus 1 because the S already canceled. When S equal to 0, we have k and 10 times and 1 per 10. 1 per 10 and 1. One per k. Only the lead system, the steady state error gonna be 10 per k, 10 per k. But when we add a lag compensator, it depends on the magnitude between the pole and the zero of the lag compensator. If you try s plus 0.2 divided by s plus 0.01, this magnitude gonna be 1 per k 20 and 1 per 10 equal to 1 per 2k, which is smaller than this. So we can tune the lag zero and pole to get the size of the steady state error for our requirement. If we consider the location, of the lead and lag network, if we consider the lead network -2 and -20, no, the pole -20, the zero -2. But for the lag network, the pole is very close to origin. Very small value. And the zero to the left-hand side, still a small value. So the effect of this one will be around here. It seems like we want to add a PI controller. We want to have 1 per S to show the pole here, but we cannot exactly do it. So we select the lag compensator instead. And it will be our system, the dominant pole is -1. For the lead compensator, we select the thing far about 20 times of -1. For the lag compensator, 0.1 is also 10 times smaller than the dominant pole, -1. It seems like the lead, we play with the thing that far to the left-hand side, but for the lag, we play with the thing that close to the imaginary axis. For the root locus, the transfer function of the original system. Is this one. 1 per S plus 1. The controller one, S plus 2 divided by S plus 20. Controller 1 is lead. The lag controller S plus 0.1 divided by S by 0.01. Lag. The open loop transfer function open loop transfer function, lead multiplied by lag multiplied by original system, open loop transfer function. And we plot the root locus. We plot the root locus of open loop transfer function. When we plot the root locus of open loop transfer function containing the lead and lag, and we just vary the gain K, the desired damping ratio 0.7. The gain that good for us is 36, and we still obtain the damping ratio 0.7. We select the gain. In order to see how is the response to the ramp input, how is the response to the ramp input? I cannot draw a straight line on the screen, sorry. It's not zero. Maybe you try to compare with this point. You try to compare with this point. Okay. With the lead lag, how can I plot the ramp response of the lead lag? I use a feedback to obtain the closed loop transfer function. To obtain a closed loop transfer function. Closed loop transfer function is the closed loop transfer function is the lead, the lag, the K, and the planned transfer function, and also consider the feedback. Closed loop transfer function is the feed forward. Feed forward means the gain K multiplied by the controller 1 or the lead, the controller 2, the lag, and the planned divided by 1 plus the loop K GC1 GC2 G. So the closed loop transfer function, you just type the command feedback, the gain, and the open loop. In this case, the feedback is equal to 1. If the sensor has transfer function, this one gonna be HS or transfer function of the sensor, and transfer function of the sensor will appear in the loop gain, but not on the feed forward gain. Again, this one, the meaning of this one, I multiply the closed loop transfer function by 1 per S because I gonna use step command for the ramp response. The reference for the ramp is 1 per S square. So I multiply 1 per S and then I use the step. And when we plot, we can see that with this lead lag compensator, we see a promising response, but we still have the steady state error, but maybe better than the lead only. Okay, I think that's all for today's lecture. Do you have any question?